Welcome back, listeners. So in the last video, we have introduced bipolar junction transistor and its basic operations. So today we'll unpack the transistor's current components and compare the three most important circuit configurations: common emitter, common base, and common collector. The learning objective today is that by the end of this video, you will be able to first identify the main current components inside a BJT, explain the difference between CE, CP, and CC configurations, and read input and output characteristic curves and pick the right configuration for the common applications. So let's start with the transistor current components. So as you observe in this diagram, this is a PNP transistor and we have given forward bias in the input terminal and reverse bias in the output terminal. So now these are the currents that are observed inside the transistor. So let's see how these currents will flow from one terminal to the another and what are the different current components. So as you can see, the current will flow from emitter to the collector in PNP transistor, and also the movement of holes are in the same direction. That means it will move from emitter to the collector. So now this I current has two components. First one is IHE and second one is IEE, where IHE is the emitter current due to holes and IEE is the emitter current due to electrons. So now these two currents will move to the base, and in base the electrons will get combined with the holes. So due to which there will be a loss. The loss due to the recombination will move out of the base. Now this loss is given by IHE minus IHC. So where IHC is the collector current due to the holes. The current that is moving inside the transistor is IHE, and out of that one current will move through the base, which will be HIB, which is nothing but IHE minus IHC. So whatever is remaining will be going to the collector, which is given by IHC. So the remaining current is IHC. Okay, so this is the current components. Now, again, we have another component in the transistor, which is due to the minority charge carriers. So now if we consider I current to be 0, that means no holes are flowing from emitter to the collector, then what we can write about IC is IC current will be due to ICO. So where ICO is the reverse saturation current. Now this ICO has two components. One will be due to holes and one will be due to electrons. So it is IHCO and IECO. So as you can see here, this is ICO, which has two components, IHCO and IECO. So this is the condition when we have the I current to be 0. Now if we have I current positive, that means it is greater than 0, then what will happen? The IC current will be having two components. First one will be IHC and ICO. Now the IHC component is equals to IHE, considering IB current to be 0. So this equation we can write it as IHE plus ICO. So now this becomes the equation for the transistor for various configurations. So what are the various configurations? So we'll be coming to that now. So the various configurations are dependent on whether we are putting emitter, base, or collector in the middle. So the overview is three small circuit diagrams we'll have from these configurations. So these are three standard amplifier configurations. First one is common emitter, Then we have common base, and finally we have common collector. So in each of these configurations, one of the terminal will be common, and based on that, we will be having our circuit. So the common refers here to the terminal which is common to both the inputs and output circuit. So each configuration has distinct input and output impedances, voltage and current gain, and typical applications. So if we give a summary, then CE would be moderate to high voltage gain and have high current gain, medium input impedance, and widely used as voltage amplification. Then CB is high voltage gain, low current gain, low input impedance, and high output impedance, common in high frequency stages. Then common collector is voltage gain equals to 1, high input impedance, low output impedance, and used as a buffer or impedance matcher. So now let's see these configurations one by one and see their responses, which we called as characteristics of the transistor. So let's consider common base configuration. So in common base configuration, the base will be in the middle and emitter will be in the input and the collector will be across the output. So now if we consider that and then connect our circuit, so it will be the emitter terminal. So the circuit will be like this. So here we have an NPN transistor. So if this is an NPN transistor where we have, this is the emitter terminal, this is the base terminal, and this is the collector terminal. So in order to make it working, we have to provide forward biasing across the input and reverse biasing across the output. So this should be connected and we should connect the supply here. So since we have here emitter is N terminal, so this should be negative. Then positive terminal connected to the base. This is ground. And this N terminal should be pulled, so we should have positive polarity here to pull the electrons, right? So this is the polarity. So the input terminal, we'll name it as PEE because it is connected to the emitter. Then the output terminal, we call it as VCC since it is connected to the collector. Now, the response in the circuit would be determined by the voltage and the current that is present in the transistor. So here, this current will be IE, which is the input current, and across the output, this is the collector current. And then the voltage across the circuit will be VEB, and across the output, the voltage will be VCB. So how we name this as VEB and VCB? So we consider as we have base in the middle, so it will be given at the end in both the nomenclature, and the other two terminals will be provided at the beginning. So it will be VEB and this is VCB. So this will repeat in all the other configurations. So similarly, if we draw the common emitter, then we'll be having the emitter in the middle. So this would be our circuit diagram, right? This is the ground terminal and the output will be across collector and emitter. So we're providing our supplies now. So now here, as you can see, this is also NPN transistor, and we have base as our input, collector as our output, and emitter as our common, which is connected to ground. So in order to give forward biasing across the input, so this should be positive terminal. Then to provide reverse bias across the output, this should be N. So N should be connected to positive terminal. And now we will be naming this as V, VB, and this will be VCC. And the voltage across this two terminal will be V. E will be common, so it will be in the second position, and B will be in the first position. Similarly, the voltage across the output will be VCE, and the corresponding currents are IB and IC. So this is with respect to common emitter. Similarly, we can also make the circuitry for common collector. So in common collector, we'll have the collector in the middle. So if collector is in the middle, then emitter will be across the output and input will be the base. So this transistor is also NPN. So if we connect the supply, then we have here P terminal. So this should be positive. Right? Then across the output, we have N terminal. So this should also be positive because we are providing reverse bias across the output. So we have input as VBB since it is base, and output is VEE. And this is ground. Common point is ground. So now this voltage will be VBC, and this voltage is VEC. Okay, and the currents are IE, and this is IB. Okay, so this is common base configuration, this is common emitter configuration, and this is the common collector configuration. So I hope you have understood the diagrams and how the polarity or the supplies are provided in the transistors, or how we bias the transistor that we have discussed. So next we will be moving towards the characteristics of these three configurations. So now let's see the common emitter configuration. So this is the common emitter configuration. So if we plot the input and output characteristics, we have to plot the response of voltage versus the current. So across the input, if we see here, we have the voltage and currents given by the x-axis will be voltage. So the voltage is VBE and the current is IB. Let's see the characteristics of the transistor in common emitter configuration. So here the transistor will not conduct until and unless the value of VBB is 0.7 or greater than 0.7. So up to this 0.7 the current will be 0, so it is 0. Then as it crosses 0.7, current will gradually increase, and it will be increasing exponentially because the input terminal of the transistor is nothing but a diode, and the diode is connected in forward bias. So the behavior of the characteristics is also similar to the diode characteristics. So this is the response of the transistor in the input. So this is the input characteristics. So now if we say want to determine this using an experiment, so what we have to do, we have to first keep the output at a constant voltage. So suppose VCC, we are keeping it at 1 volt, and then what we do, we increase the voltage VBB. So by increasing the voltage VBB, the response will be given as this, right? So now this is considered as VCC equals to 1 volt, or also we can name it as VCE1. Okay. Now if we increase this voltage to suppose 5 volt, then what will happen to the characteristics? So if we increase it to 5 volt, then also we are going to get the same characteristics, but the thing is whether our current will be increasing or decreasing. So as we increase the output voltage, then what will happen? So if we go back to the block diagram or the transistor drawn as a block, so what we have discussed here, the electrons will move from emitter to the base, and then it will move to the collector, right? This was the movement of the electrons. Now if we increase this pull, we are increasing VCC means we are increasing this pull. Pull means we are increasing this supply. If we are increasing this supply, so we are going to pull the electrons more from base to collector. So if that is the case, the current IB will fall, correct? And the current IE and IC will increase. So if IB is going down, then the response of the IB will be lesser if we increase the value of VCE. So that means suppose we are getting a current of around, this is suppose, let us consider 2 milliampere. So we are getting 2 milliampere across this point, which would be around suppose 0.75 volts. Now in the second case, whenever we are increasing the value of VCE1, then what will happen? It will attain a lower amount of current, because as the pull increases, IB decreases. So that means it will be somewhere around here. So which will be, suppose let us consider 1.8 milliampere. So if that is the case, then the graph will be changed to this, right? So this is VCE2. So as we have understood, as we increase the output voltage, the input current decreases. So if input current decreases, then the response shift towards right. So this is the input characteristics of common emitter. So now let's see what will be the input characteristics for the common base. So now moving ahead to the common base configuration. So let's see what will be the characteristics in case of common base. So we are discussing the input characteristics first. So like last example of common emitter, let's draw the x-axis and y-axis. So now the x-axis will be, as we know, it is voltage, and the voltage is VEB, right? And the current across the input is IE. So let's see what will be the behavior. So as we already know, it will behave as a diode. So the current will increase
like that characteristics, and for a output CB1. Now CB1 is suppose initially 1 volt. Now if we increase CB2, or if we increase CB to a next value, suppose 5 volt, then what will happen to the characteristics, whether it will move right or left. So moving on to right or left is dependent on IE. So let's see what will happen to IE. So now if we again draw the transistor, emitter, base, collector. So as we have discussed, if we increase the pull, then IB current decreases, right? So if IB current decreases, then the transistor current equation as we know is IE equals to IB plus IC. So if IB decreases, then obviously value of IE will increase. So initially if we have a current across this point, next time we will be getting the current into a higher value, or next time we will be getting a higher value current. So that means the graph will be shifting towards right. So this is VCB2, suppose 5 volt. Okay. So this should be coming like this. Sorry for the mistake. As we know the characteristics. So the current should increase gradually, right? And it should start after 0.7. That condition will remain same. But the thing is, next time we will be getting higher values of current. So as we increase the output voltage, the graph shifts towards left. So this is the response of the common base. Now if we see similarly for common collector, then here also we have base across the input, emitter across the output, and collector in the middle, or collector being common. So here also if we draw the characteristics, then now input current is IB and input voltage is VBC. This is that characteristics, which is same as the input characteristics of the transistor. So this is across some voltage VEC, suppose 1 volt, EC1. Now if we increase EC1 to 5 volt, then what will happen? As we have already discussed, as we increase the collector current, the value of IB decreases. So if value of IB decreases, that means graph will shift towards right. Okay, so this is VEC2 at 5 volt. Okay, so this will be the characteristics for the common collector. Now let us move towards the output characteristics and how it will look like. So for the output characteristics, let us consider common base configuration first, and let's use another color to identify the output characteristics. So now let's see what would be the voltage and currents. So the voltage across the output in common base is given as VCB and the current is IC. Now here what will happen? So as we are changing the value of IE current, what would be the response? So initially let us consider we are getting IE current as suppose 100 microampere or 0.1 milliampere. Now the current equation is given by IE equals to IB plus IC. Now if we consider IB is negligible, then we can eliminate this. Then IE equals to IC. So if this is the case, then output would be, as we know, I equals to IC means this will be the response. So let us consider this is the response across IE1. So IE1 is suppose 100 microampere, right? So if base current is 0, then whatever is moving in through the emitter, same amount of electrons will go to the collector. So I equals to IC. So now if we increase the input, then the input current will also increase. If the input current is increased, then the output current is also increased because both are same. So the IE2 plot will be here. Suppose around that 300 microampere. Okay. So this is the response of output characteristics of the common base configuration. So now let's move ahead to the common emitter configuration. If we plot, then the current, the voltage. So let's see what are the voltages and the currents. So the output voltage in common emitter is given as VCE and the output current is IC. Now here the input current is IB. So for a particular input current IB, what would be the IC current if we increase the output voltage? So now if we again see the transistor functioning, we have emitter, we have base and we have collector, right? Now the input current is base. So as we increase this pull, the base current decreases. So if base current decreases, the collector current will increase more. As we know, IE equals to IB plus IC. So if base is going down, then IC will be going up. That means it will increase. But after a particular period of time, what will happen? It will not increase to a higher extent, because as we consider, we have 10,000 electrons here. So if IB is at a value of suppose 50 microampere, right? That means it is allowing a particular values of electrons. So let us consider suppose it is sending 2000 electrons. So this 2000 electrons will go to the collector and their movement will depend on this positive polarity. So the supply that we are connecting in between base and collector, as it increases, the electrons will also move towards the collector. How many electrons? So it should be 2000, but not more than 2000 because base is allowing only 2000 electrons. So the graph will be, it will be increasing, and then after a certain time, the increase will be slowing down. So this is suppose at a current of IB1, which is given as 50 microampere as we have considered. Okay. Now what will happen in the next value? That means if we increase IB further, so if we increase IB further, that will be IB2, suppose 100 microampere. Then what will happen? Instead of 2000, now we will be sending 3000, or as the number is doubled. So for 50 becoming 100, 2000 will become 4000. Now since the number of electrons are increasing, so now if we increase the output voltage, then this electron movement will also increase and we'll have more amount of current. So if we plot it, so the current will increase, and after a certain time, in rate of increase in current will be lowered. So this is the value of IB2 at suppose 100 microampere. Okay. So this is the response of common emitter configuration, and this is the output characteristics. So I hope you have understood the characteristics of input and output, common base, common emitter, and we have also discussed common collector. So now for the common collector, what would be the output response? You consider it as a homework and tell me whether your response will be increasing or it will be constant. So you have to identify or you have to determine whether your output current is remaining constant or whether your output current is increasing. Okay. So this is the characteristics of the transistors. Let's first summarize. So this first one is the common emitter configuration as we have seen here. So this is the common emitter configuration. The input and output terminal both are connected to the positive and negative of the supply, and then these are the responses, that is the input characteristics and the output characteristics. So as the IB current is the input, so as we increase the output voltage, the IB current decreases, so the graph shifts towards right. So for the output characteristics, so initially the current will increase and then later the rate of increase will be reduced and the graph will take this shape. And as we increase the input current, the output current also increases. So this was the common emitter configuration. Similarly, in case of common base, we have negative supply and positive supply. The input is connected to negative supply and the output is connected to the positive supply, maintaining forward bias and reverse bias across the input and output terminal. And we have the input characteristics as the I current, as we are having, as we increase the output voltage, the I current will increase. So the graph shift towards left, and across the output, if we see, since we are in common base configuration, and in common base configuration, if IB current is negligible, then we can neglect the value and IE becomes equals to, as we know, IB plus IC. Since we are neglecting IB, so IE equals to IC. So that is why whatever input current we are getting, that current will remain constant across the output, and it will increase if we increase the input current. So these are the common emitter and common base configuration. So now let's see the current relation. The current relation, as we already know, is given by IC equals to IHE plus ICO. Now this ICO is the reverse saturation current and this is in the current gain. So if we determine the current gain, then it is the ratio of output current to input current. So in common emitter configuration, we have output current as IC and input current as IB. So this is given by beta. So beta is the current gain of common emitter configuration. Now for common emitter configuration, this equation changes to IC equals to, this is gain, so which is given by beta IB from here, and the reverse saturation current ICO. Now since we are in common emitter configuration, so ICO will be termed as ICEO. Okay. So these are the current components for common emitter configuration. So now coming to common base configuration, again we have IC equals to IHE plus ICO. Now here ICO will become ICBO because we're discussing common base and this is the gain. So let's see what will be the gain. So in common base, the gain factor is called as alpha. So alpha is the ratio of output by input. Output is IC, input is IE. But as we know, IE current equals to IB plus IC. Now IE equals to IC if IB is 0. If IB is 0, right? So that means this current will be equals to IE only when IC is 0. So if that is the case, the maximum value that alpha will attain is 1, right? So from this equation, IC equals to alpha times IE. So now we can put it here, alpha times IE plus ICBU. So this is the current equation of common base. And this is the current equation of common emitter. Okay. So similarly, you determine the current component for the common collector, as you have to determine the responses and the value of the current. So I am giving you a hint. You try to identify this. So IE is given by 1 plus beta IB plus 1 plus beta CBO, where this is given as CCO, or IE is 1 plus beta IB plus ICCO. Okay. So you try to find out this. Now next, let us see what is the relation of alpha, beta and gamma. So we have not defined what is gamma. So the gain in the common collector configuration is called as gamma. So the gamma is given by the ratio of output by input. Okay. So now let's see what is the relation between alpha, beta and gamma. As we know, alpha is given by, this is found in common base configuration. So which is IC by IE. So now if you want to determine the relation of alpha and beta, so first let us break this term into IE is IB plus IC. Now if we take 1 by alpha, then the numerator and denominator will change this position, and this is given as IB by IC plus 1, which is 1 by alpha. So now this one term, let us bring it here. So this is alpha times 1 minus alpha is IB by IC. Now as we know, IB by IC is nothing but 1 by beta, because beta is IC by IB. So this implies, so the value of beta is given by alpha by 1 minus alpha. So this is the relation of alpha and beta, or beta in terms of alpha. So now if you want to determine the other way around, that is what is alpha in terms of beta, so then let us consider beta, which is given as IC by IB, right? Now we want this in terms of alpha. So alpha is given by IC by IE. So we have to replace this term IB. So IB will be given as IE minus IC. So now 1 by beta is IE by IC minus 1. Now this is 1 by alpha minus 1. So now 1 by alpha is 1 by beta plus 1 equals to 1 by alpha. So which implies alpha is given by beta by 1 plus beta. So this is the relation of alpha in terms of beta, right? So I hope you've understood the conversion. So similarly, if we see the gamma is given as IE divided by IB. Now, if we want to determine it in terms of beta, then the beta is given as IC by IB. So now here, if we break this IE term, it will be IB plus IC divided by IB. So which is equals to 1 plus IC by IB. So IC by IB is beta. So gamma is 1 plus beta. Okay. So these are the conversion of alpha, beta and gamma. So alpha is beta by 1 plus beta. Then moving ahead, beta is alpha by 1 minus alpha. So these are the relations of the gain. Now from the gain, as we have observed, the gain alpha is IC by IE. So since IB is negligible, so the value of this component will be maximum as 1. So if the value of the gain is 1, or it cannot attain, the circuit cannot attain more than one gain, so that means we cannot use this configuration as amplifier. So common base configuration is not suitable for amplification. Now the value of alpha, if we see for various transistors, then it will be below 1. So the ranges that we obtain are around 0.98, 0.99 or 0.97. So these are the ranges of the value alpha. Now coming to beta, beta is IC by IB. So now a small amount of current in IB changes a higher extent of IC current. So that means this gain is very high. So typically this gain ranges from 100 to 500 or 600, right? So this is beta with such a large gain. So that is why this circuitry is preferred for the amplifiers. So next, if we see gamma, so gamma is IE divided by IB. So the gamma term is higher than the beta term, and the gamma is given by 1 plus beta. So if beta is 100 to 500, so gamma will be plus 1. So that means we can also use this circuit as amplifiers because the gain is high. Okay. So I hope you have understood today's class. So in the next class, we will be looking forward to various practical examples where the transistors are used. So keep joining our classes and do subscribe so that you don't miss any content. Thank you for joining.